Okay, everybody, we're going to go through Chapter 10. In this video, I'm just going to cover things from 10.3 because our homework has us do that section first. 10.3 has to do with two proportion z tests and two proportion z intervals. All right. 10.1, which is what the homework is labeled as, but it comes second in the homework. It has to do with finding the means, and so therefore t-tests and t-intervals. But in this video, we're going to focus on proportions. So again, the homework is having us do 10.3 before 10.1. I think it's mainly because the proportions are actually a little less ugly. You'll see some ugly formulas coming up, but it's easy. Just plug and chug the numbers into them, or let StatCrunch do the heavy lifting. Okay, so this is going to be nearly identical to what we did in Chapter 8 and 9 for one proportion. In Chapter 8 and 9, we did one proportion intervals and one proportion tests. Here we are doing two sample methods, and so what we are using this for is comparing two groups. Okay, we're going to use this when we're trying to compare two groups. All right, so again, we are focusing in this video on proportions. Okay, so there are two things we're going to do, either a two proportion z interval or a two proportion z test. Again, just depending on what it is you're trying to do. Remember, intervals are used to estimate a number. Right, and in this case, the number we're looking for would be a proportion. And tests are used to test a claim. Okay, but again, the processes we laid out in Chapter 8 and Chapter 9 are exactly the same as what we're doing here. This just kind of expands, it kind of opens up our ability to answer some more in-depth questions. So here are some examples of questions about proportions that we can answer. Are men more likely to drink? Are men more likely than women to drink black coffee? How much more do Democrats support the Affordable Care Act compared to Republicans? Is the proportion of 36 to 45-year-old drivers that have been in an accident within the past year lower than the proportion of 16 to 25-year-old drivers that have been in an accident within the past year? Okay, so again, what it's giving us the ability to compare two groups, all right? Either a proportion among them or what we'll see next video, a mean. So anything with a mean, I'm just going to skip for right now because again, that's 10.1 material. That's not what this video is going to talk about. So I'm just going to skip over those problems. Okay, so sort of a key notion here. How do we compare two values? So whenever you want to compare two things in mathematics, typically we look at the difference between them. And so again, either the difference in the means of two groups, or in our case for this video, the difference in the proportions for two groups. All right, so if we want to analyze this, the difference of two proportions, I want to kind of probably figure out, well, does it look normal? And if it's normal, what would be, sort of the standard deviation and mean of this thing? That's what we want to try and figure out, so we could then begin to do probability, find area under the curve. Well, here's the standard deviation of the difference between two observed proportions. And we learned back in Chapter 7, and we've been using it in Chapter 8, that the standard deviation of a sample proportion, isn't it just PQ over N, all square rooted, right? Well, all we've got now is we've got a proportion from sample 1 and a proportion from sample 2. If I'm looking at the standard deviation of their difference, it's basically like I'm adding up the standard deviation from proportion 1 and adding it to the standard deviation of proportion 2 in a way. Don't get confused by the fact that here we're subtracting and here we're adding. Remember, standard deviation kind of measures the amount of fluctuation or sway that our data values land from the middle or from the mean. And so I don't really want to be subtracting that because then they might cancel out. I sort of want to be adding up all the amount of fluctuation we can have to get a total overall amount of fluctuation from our true proportion. Okay, so if you don't, and also they kind of give a note in here, which they did in chapter 8 and 9, if you don't know population parameters like P and Q, you can use the estimates, P hat and Q hat, and it won't cause much of a ruckus in your answer. In other words, it's pretty safe to use P hat and Q hat in place of P and Q, which were the actual population parameters. Now, because the standard deviation here does not depend on S, like a standard deviation from a sample, we don't have to worry about using t intervals or anything, or t values. This is all z inference procedures. So z intervals and z tests are what we will use when dealing with proportions, just like we learned in chapter 8 and 9. When we get to means, and that standard deviation is dictated by the standard deviation of the sample, that's when we have to switch over to t statistics. So that'll be in the next video. Speaking of the next video, that's where we'll talk about this. This looks awful. I get it. It's really not awful. Well, we'll go through it in the next video. So again, this is 10.1 that we'll just wait and come back to. It looks a lot worse than it is. But let's take a look at this problem here. Example 1. It says 48% of 500 students randomly sampled from College A drive to school. 67% of 625 students sampled from College B drive to school. Estimate how much more of a proportion of students from College B drive to school compared to students, or the proportion of students from College A. Ugh, it's a mouthful. Okay, so what they're saying is, they're saying that there's some true proportion of students that drive to College B. A, let's start with A. Okay, there's some true proportion or some true percentage of all the students at College A that drive to school. From the sample, it looks like more students drive to College B, so the true proportion of students that drive to College B is probably higher and to the right. Well, what this question is asking for is, it says estimate how much more of a proportion of students from College B drive to school compared to the proportion from College A. In other words, they're asking us to find this distance here. They want to know, what is that? How much more or higher of a percentage do the students of College B drive to school compared to College A? All right, and so what we did is we took a sample, and we found a sample from College A. Maybe that was a little above or below, but it should be pretty close to what the true proportion for College A is. And we took a sample from College B, and so we got some p hat from College B. Again, maybe above or below, but probably pretty close to what the true proportion for College B is. So here's what our guess is. Our guess says there was 48% at College A and 67% at College B. So if I were to subtract those correctly, I think that's 19% difference. So our guess is about 19% difference. Okay, but we know that guess is probably a little off because our samples were off from the true proportions. So what we want to do is, I'm jumping the gun, I should have asked, is this a confidence interval or a hypothesis test? That's what we should have asked first. Because in the beginning, it's really hard sometimes to distinguish which of those procedures you should use. What jumped out at me is it says estimate. Estimate how much more. So we're looking for a number. That means we're using a confidence interval. Remember, confidence intervals estimate a number. So anyways, I've got this estimate or this guess. I think it looks to me from my sample that 19% more students drive to school at College B compared to A. But what we're going to want to do is build a window around it. Again, create sort of add our margin of error left and right from that guess so that we hopefully scoop up the true difference, hopefully lives somewhere in that window. Okay. Well, the 5 steps for confidence intervals and hypothesis tests are exactly what you've already learned. So nothing is changing from chapter 8 and 9. The only thing that changes is the ugliness of the formula in step 4. And it's not even that ugly, especially if you're using StatCrunch, then it doesn't matter at all. And step 3 got twice as tedious because now you have to verify IRL for both college A and college B, or the samples from each one. So that's a little annoying, but the procedure itself has not changed at all. So first step for a confidence interval is write out what you want. We want the proportion of students from college B minus the proportion of students from college A that drive. The difference in proportions of students that drive the difference in proportions of students that drive to school at college B versus college A, I guess. I'm sure we could phrase that probably better, but just kind of stating what we're looking for. And they don't give us a confidence level here, so it's up to us. How about at 95% confidence? If they don't give you a confidence interval or a level of significance if you're doing a test, personally, I always stick with 95% for my confidence intervals and 5% for my alpha, my level of significance. I think those are good, well-rounded numbers that you'll always do fine by. Okay, 2 is name the procedure. What we learned is how to do a 1 proportion z interval. This is a 2 proportion z interval. 2 proportion z interval. All right, step 3 is again check IRL, independent, random, large enough. And this time for large enough, what we mean is for p hats from college A and the p hats from college B to be normal. All right, independent. Well, let's see. Let's maybe assume that these are very large colleges. So I think it's safe to assume that from college A we sampled 500 students. Let's assume that that's less than 5% of all students at college A. And same, I think we could just kind of assume this is a very big college. So let's assume that that 625 is less than 5% of all students at college B. And so we can treat as independent. So like I said, it's the same exact step we did earlier. It's just a little more annoying now because now I got to check it for both samples I'm taking. So they do use the word randomly selected. So yes, a random process was used, or a random sample was taken. So we're good there. Now large enough, remember for proportions, the number of successes and fails has to be greater than 10. And we got to do that for college A. So the number of success, which is n times p, well, we sampled, let's see, we sampled 500, that's my n. The percentage that drove was 48%. So that's over 10, but let's see what that is. It's 240. So we're good there. We're greater than or equal to 10. And then the number of fails would be NQ, or if you sampled 500 people and 240 drove to school, then that means the rest didn't. 260 did not drive to school. That's also greater than or equal to 10, so we're good. So college A works. The sample proportions will be normal, or approximately normal. Same deal for college B. Number of successes, which is n times p. College B, we sampled 625 and 0.67 drove to school. So that's 418.75. So let's just say 419. Definitely over 10. And if all the rest didn't drive, then the fails, which you can actually just plug in n times q, or just take 625 minus the 419 that drove, that's 206. So that's greater than or equal to 10. We're good there. All right, those are all greater than or equal to 10. So the sample proportions themselves are normal, or approximately normal. All right, so that took up a lot of space. Let's do step 4, which is where you actually find the confidence interval. The format is identical. Remember, for any confidence interval, isn't it your point estimate? Let me just see if I could do this. Estimate plus or minus the margin of error. And the margin of error, if you recall, is your critical z-score, or t-score, depending on if you're doing means or proportions, times your standard deviation. So I'm going to take the general form would be my point estimate, the sample proportion from college B minus the sample proportion from college A, right? Remember that right there is my guess, my estimate. I'm going to add and subtract my margin of error, which is my critical z-score, times the standard deviation. And we just learned that the standard deviation for these proportions is pretty much like what we learned in Chapter 7, except now that there's 2 of them, I combine all the standard deviation together. It's the, it'd be the sample from college B in college, hold on one sec. It'd be the percentage that drive from college B times the percentage that don't drive from college B over the number of people from college B we sampled, plus the percentage that drive from A times the percentage that don't from A over the number of sampled from A. And these do represent the true population percentages, but we don't know them. You can always use the sample percentages we found. So these can all be hats, p hats and q hats. And that's fine. Just plug and chug. I mean, I've got these numbers. So PB minus P hat A. So at college B, we saw 67% of our sample drove to school. College A, it was 48% of the sample drove to school. My critical z-score for a 95% confidence interval, if you recall, that's a 1.96. And so for college B, the percentage that drive was 0.67. So 0.33 did not drive, and my sample size was 625. And for college A, it was 0.48 drove, so 0.52 did not drive over a sample size of 500. And I'm going to pause this while I type this all into my calculator, and I'll tell you what I get. Okay, if I typed it all in my calculator right, well, let's do StatCrunch after this to verify, but this is what I get. Okay, and so what that window represents is that represents the difference in the proportion of students that drive to college B compared to college A. So this is between 13.3% and 24.8%. We would say that between 13.3% and 24.8% more of the students at college B drive to school than compared to college A. All right, so again, let me just this is my window up here, 0.133 and 0.248. So since I'm out of room, I'm going to come up here and interpret that. We are 95% confident that between 13.3% and 24.8% more students drive to college B versus college A? Right, so at college B, more of their student population drives to school. How much more? Between 13 and 24.8% more drive to school as compared to those students at college A. So I hope you see that the process was like identical to what we did in Chapter 8. Some of the steps just got twice as long because now we have 2 groups as opposed to 1. But my confidence interval still has the same format, estimate plus or minus margin of error. It's just that my estimate is the difference between 2 proportions, and my margin of error got doubly ugly, or the formula got twice as ugly just because I got twice as many things in there. But plug and chug. Let me show you this on StatCrunch real quick. Let's just get those numbers. I believe I have it ready to go. Yep. So remember, to do a confidence interval or a z-test, you go to confidence interval or a hypothesis test. Go to stat, and you're either going to click on z-stats, t-stats, or proportion stats. Remember, these first 2 have to do with finding means, okay, or a test on a mean, and you would use z if you know the population standard deviation. Most likely you'll use t because you're most likely using the sample standard deviation. We are doing proportion stats, so I'm going to go to proportion, and the only difference here is we don't hit 1 sample, we say now we got 2 samples. I do not have data. Again, data would mean there's a column or 2 columns of data with actual raw numbers in it. We have a summary of our data. So they just want me to tell them about sample 1 and sample 2. What I need to do is just make sure that I pay attention to who is first. So this is preloaded. I'm doing a confidence interval down here. It's preloaded with P1 minus P2. And the way I did the problem, I put college B first. I took the percentage at college B minus the percentage at college A. So 1 should be college B. So at college B, we observed 625 folks. The number of successes, actually it came out to a decimal. I just rounded, so let me just double check. 625 times 0.4, 14.75. So I'll just give it exact. College 2, we observed 500 people, or at College A, we observed 500, and the number of successes was 240. 240 those guys drove to school. Confidence interval, so that's B minus A at 95%. Let's see. All right, there's the lower limit, 13.133 if they round it, right, what we got, and 0.2472. We got 0.248, all right? So again, StatCrunch is a little bit more accurate, but because they're using a better critical z-score. But anyways, not bad. So that's how we could do a confidence interval for 2 proportions on StatCrunch. It's the same way we did it for 1. Again, you just go to 2 sample with summary and tell it about both of your cases. Again, just do pay attention to which one is going first, okay? Which one should be sample 1 and which one should be sample 2. It doesn't matter either way because it all comes down to ultimately how you interpret it in step 5, but you need to pay attention to the order regardless. All right. So what else do we need to do here? Okay, so we did a confidence interval. This next page is a confidence interval for mean, so we'll skip and come back to that. Okay, we'll do that in the next video. Here they're then going to talk about performing a hypothesis test. Okay, and so they start us just having to practice write the hypotheses, and then on the next page we actually do a hypothesis test, and that will be it for this video, because then the rest of the stuff from the notes have to do with means. So I'll make another video about the means. But let's give this one a shot and then we'll try that hypothesis test. So this says that 42 men and 54 women were randomly selected and asked if they prefer vanilla or chocolate. 27 men said that they prefer vanilla, and 28 women said that they prefer vanilla. Is there a difference between the two genders? Okay, so this maybe help to clarify. Let's let P equal the proportion that prefer vanilla, or percentage, whichever word you want to use. Okay, let's let P represent the proportion that prefer vanilla. And so we're doing a hypothesis test now, right? It's not asking us to estimate a number. It's asking us basically a yes or no question. Is there a difference in the preference between the two genders? So is there a difference among men and women and their preference for vanilla ice cream? Okay, so let's write out the null and alternative hypothesis for this test. The null hypothesis, again, is generally the status quo, the baseline. It always uses equals, right? So the null hypothesis would be that the proportion of men that prefer vanilla over chocolate is the same as the proportion of women that prefer vanilla over chocolate. Okay. Again, doesn't the hypothesis or the null hypothesis always use an equal sign? And the alternative always uses the same parameter notation, but then it's got to make a choice between those three symbols. And I mentioned in other videos or in the lectures that we kind of prefer those if you have one way, if you have an inkling over one way or the other. But to me, this question just is going to be the not equal case. It just says, is there a difference? So doesn't say, do men prefer vanilla more than women or vice versa. It just says, are they the same or are they different? So to me, this is a not equal case. So that's one way to write up your null and alternative hypotheses. Or, and really this way is the more common way you would see it, takes that same idea, but take this equation here and just get everything on one side. Can you imagine just moving the P sub W, or the proportion of women that prefer vanilla, to the other side here? And wouldn't you get the proportion of men that prefer vanilla minus the proportion of women that prefer vanilla equals 0, right? It's like I just shuffle, just like an algebraic equation. I move that to the other side, leaving 0 on the right and P sub M minus P sub W on the left. Sorry. Oh yeah, on the left. And then same for my alternative. So again, this tends to be sort of a more common way of writing out the null and alternative hypothesis. Basically comparing them to 0. Okay. All right. Well, let's try part B. It says, oh, this is back to the driving example, so they're going to actually have us make a test out of it. It says 48% of 500 students randomly selected from College A drive to school. 67% of students sampled from College B drive to school. Is the proportion of students at College B who drive to school more than 10% higher than the proportion that drive to school from College A? So again, this is not a confidence interval because they're not asking you to estimate the difference. We already did that. They're asking me a yes or no question. Is the proportion of students at College B that drive to school more than 10% higher than the proportion of students at College A? So again, it's a yes or no question, so we're doing a hypothesis test. So my null and alternative hypotheses here, and again, these take some practice. Well, the null always uses equals, right? And we just kind of mentioned that of these two choices, it's a little more preferred to have the proportions on the same side of one another. So it actually doesn't matter which one goes first. You just have to pay attention to that when it comes time to writing your alternative. So the question is is the proportion of students that drive to college B more than 10% higher than the proportion that drive to college A? So if I take the proportion of B students minus the proportion of A students, the status quo would be that it's exactly 10%. The alternative would be that it's higher than 10%. Now, again, this is one place you got to be very careful. Oops, so there's higher than 10%. What if instead I had put, sorry, hold on one second. College A first minus college B. All right, the null would be that there's a 10% difference. But here's the thing, if I think that college A is higher, college B is higher, I think this is a bigger number, then if I take A minus B, wouldn't that be a negative value, right? Because B is a bigger number. The percentage of students that go to college B is bigger. And then my alternative, the probability of A minus probability of B compared to that number, this can get tricky because it kind of tends to flip the inequality sign. Because here I'm trying to determine if B is bigger than A by more than 10%. Meaning if it is, like say 15%, then if I were to reverse the order here, this would actually need to be even smaller than this. It would be like maybe negative 0.15. Both of these tests would absolutely work. I think this one's a little more intuitive, put the big one first. But both of these tests would give us the same result at the end of the day. We would either correctly reject the null or not reject the null. So you just got to be careful and keep an eye on who's bigger than who. All right, so really pay attention to those values. All right, let's take a look at this next problem. Okay, give me 1 minute. Okay, let's perform a hypothesis test here. And on that same question of men and women who prefer vanilla. And I want to take a minute and talk about this. So let's read the problem. It says 42 men and 54 women were randomly selected and asked if they prefer vanilla or chocolate. 27 men said they prefer vanilla and 28 women said they preferred vanilla. Okay. Is there a difference between the two genders? So let me just first get some sample numbers going down here. The percentage of men that from our sample that preferred vanilla was, out of 42 men, 27 said they prefer vanilla. So that is 0.643 if I round it. The percentage from our sample of women that prefer vanilla, well, there were 54 women asked. 28 said they do. 0.519 if I round it. Okay, so there's my sample proportions for men and women that prefer vanilla. So we're going to do step 1, which is to list out the null and alternative hypotheses. Step 2, name the procedure. Step 3, check for good statistics. And then step 4, and I think I'll come back to this at step 4. So let's start with the step 1. What is the null and alternative hypotheses? And we just did this on the previous page. Again, the question is asking is there a difference in the two genders and their preference for vanilla? And so we said that the preferred way to write that first null hypothesis was that the difference between men and women that prefer vanilla, well, the baseline is that there is no difference, that the difference between them is 0. Write this a little more clear. Okay. And again, it's not like I had to put the percentage of men first or women first. It wouldn't matter, okay? Especially in this case where it's a not equaled case, a two-tailed case. It does make a little difference when it comes to picking these symbols, and you just got to make sure you grab the right one based on who's bigger. we said the alternative is that there is a difference. So if I take the difference between these two percentages, the percentage of men and women that like vanilla, the null is that there's no difference between them. The alternative is that there is a difference, that it's not 0, that there is some distance in between them. They're not the same number. Let's go ahead and let alpha, our level of significance, be good old 5%. The process I'm doing is a 2 proportion Z test. All right. And let's check for independent, random, and large. Large enough for our p-hats for men and p-hats for women to be normal. Well, approximately normal. Okay, independent. Well, we only sampled 42 men. That's definitely less than 5% of all men out there that eat ice cream, save for women. Okay, so, oh, I didn't even say ice cream, huh? Just the flavors. Anyways, 42 men is less than 5% of all men, and 54 women is less than 5% of all women. So we can treat as independent. Okay, good old 5% rule. It does say a random process was used. Okay, random sample was taken. And lastly, are we large enough? So our p-hats for, well, let's look for men. Let's see, so for men, we need the number of successes, which is n times p, to be greater than 10. Well, actually, I could figure out what p is. In fact, there's p. We did it there. And I could multiply it by the 42 men that we sampled. Or it just says that 27 men said, yes, I prefer vanilla. Well, that's more than 10, so we're good. And if 27 men said they preferred vanilla, and I asked 42, that means the rest said no. So that would be 15. For women, again, number of success. Well, they told us that 28 women they asked prefer vanilla. So they had 28 successes. So they're more than 10 there. And then the number of fails. Again, they asked 54 women. And if 28 said, yes, I prefer vanilla, then that would mean 26 said, no, they prefer chocolate. Either way, we're bigger than 10. So, yes, large enough for sample proportions of mean for men and women to be normal. Approximately normal. Yikes. Okay. So, step 3 got a little more tedious. It was already tedious. Okay, let's talk about step 4. Because remember, for a hypothesis test, isn't the idea now to find your test statistic and then your p-value? Right? And so we want to first find our test statistic. Okay. And in general, the form of our test statistic, actually, let me write this out here. I'm just going to write it. I'm not going to write out all the notation, but remember, it's what we observe minus what was claimed, all divided by the standard deviation. Right? Isn't that the general form for any test statistic or any z-score or critical score? It's just that these things have now gotten a little bit uglier. Because what I observed was the difference in these two sample proportions. So I observed a difference of, if I take, again, I'm looking at the percentage of men minus the percentage of women, okay? So I'm looking up here at my sample proportions or percentages I found. So I observed 0.643 minus 0.519 to be the difference in those two percentages or proportions. The claim is that there is no difference between them. So the claim is 0. All right. Now, for the standard deviation, let's talk about this for a second here. So they add this little bit into the notes, and this does help make things a little more accurate. It says if you're doing this by hand, pay attention that the null hypothesis assumes that the proportions are equal, right? Or that there is no difference between them, okay? If the difference between them is 0, they are equal. Remember, you could shuffle that percentage of women that like vanilla over to the other side and you'll get this statement. So if that's the case, it says we prefer to use a standard error or standard deviation that also uses that assumption that they are the same. And so what they will do is they will pool the proportions, okay? So instead of your standard deviation looking like this, where it's the proportion of men and the percentage of men that like vanilla times the percentage of men that don't over the number of men, plus the percentage of women that like vanilla times the percentage of women that don't over the number of women, right? Instead of keeping it separate with men and women, because the assumption is that they're the same, the percentages of men and women that like vanilla are the same, they will combine them and stop looking at them as men and women and just look at them as people. So what they do is they still give the same format, PQ over N1, PQ over N1, but this isn't the P for men and Q for men and P for women and Q for women. The sample sizes are, but P is found by adding the men and women together and dividing by the number of men and women that were sampled. So I'm going to do this by hand here, but I would stop doing any of this by hand and use StatCrunch. I'm only going to show you here. So they give it a P bar just to give it a different symbol, all right? But I first need to figure out what's that combined proportion of people that prefer vanilla compared to chocolate. I don't know if you could hear, it's Christmas in May here. I don't know if you could hear in the background. Hold on one second. Okay, so let's find this p-value, or this proportion, not a p-value, this proportion that I will then use to find the pooled standard deviation, which is going to go right down here, okay, the standard deviation for this pooled data. So again, what I want is the number of men and women that like vanilla. I need to add that up. 27 men, 28 women, and divide that by the total number of men and women sampled. 42 men and 54 women. And what the heck is that going to be? That is 0.573. So that is the percentage of people that prefer vanilla, men and women combined. And then therefore the complement of that, Q, would be 0.427. That is the percentage of people sampled that do not prefer vanilla. Okay, so again, not men and women, but just people in general. They're pooling those results together. And so they'll use those P and Q values when doing the standard deviation. They're pooling the data. So what I would write out here would be 0.573 times 0.427 over the number of men sampled, which was 42, right? That's over N1. Plus that percentage again, 0.573 times 0.427 over the number of women sampled, which was 54. That right there is my z-score. Okay, let me pause it and put that in the calculator and see what I get. Okay, if I did it right, I got 1.22, all right, roughly. So that's part one of the process, is find your test statistic, and now part two of that process is find the p-value. Now, because this is a two-tailed test, right? Because I'm looking for not equals, what I've got is a two-tailed test, and my p-value is actually the area that is outside a negative 1.22 and outside a positive 1.22. So my p-value is really this area here. Now those are just standard z-scores, so I can find those on a z-table, no problem. Just to save some sanity, I'm going to go ahead and just run it on StatCrunch. So, or StatCrunch. I mean, I would have just done StatCrunch from the get-go instead of doing all this stuff by hand with step 4. But again, we've done this before. You know, we started doing that back in chapter 6, finding those areas. So you could do that on a z-table. But just, you know, contact me if you need help with it. Let's go to StatCrunch and run this hypothesis test. So here's how I would have done step 4. Proportion stats, 2 sample with a summary. We're doing a hypothesis test this time. Now, notice they always put P1 minus P2, sample 1 minus sample 2. Just to match the work I did, I put men first and then women. So men minus women. It does not matter, and you could do it either way. I'm only trying to keep this consistent with the work I wrote down so that any numbers that may match up will look right, not opposites of one another. So sample 1, I'm going to put the men's information here. So we observed 42 men, and the number of successes was 27 men said they prefer vanilla. For the women, we observed 54 women, and the number of successes, the number that preferred vanilla, was 28. All right, we're doing a hypothesis test this time, not a confidence interval. The null is that there is no difference, that the difference between the percentages of men and women, the difference between them is nothing, meaning they're the same. Or that there is a difference, so the difference between them is not 0, meaning it's something else, that there is a difference. Again, this doesn't test to say that men like vanilla more than women or women like it more than men. This is just going to say there's a difference. You would need to use an inequality symbol to figure out that other question. Okay, let's hit compute. Oh, you know what? Let me just do it again, and we'll just put up the graph. Not needed, but let's just put up the p-value graph. So here's what we got. We've got our test statistic. That's like about what we found, right? 1.22. It's good. And there's our p-value, all right? And that is the combined area left and right of, again, here's negative 1.22, and we wanted the area left. Here's positive 1.22, and we wanted the area right, because it's a two-tailed test. That combined area is our p-value, right? The combined area is the p-value, and it is 0.2218. So if you were to look these up on the t-table, you'd get about 11% for each of these tails. Okay, 0.2218. So here we got a p-value of 0.2218. All right, so how do we interpret this then? Last step is interpret our results. The lowest percentage we were comfortable going with, we said, was 5%. We went with alpha equals 5%. So again, that would have been the likelihood that, you know, that if men and women truly do like vanilla flavor the same, that there is no difference between the percentage of men and women that like vanilla. If that's true, well, we did get a little difference in our sample. Okay, so the question we need, or the point of this test, was to determine, is that difference that we found, because there is some difference there, is that just normal fluctuation of statistics, Or was that a substantial enough difference to suggest that the null is wrong and that actually the alternative is right, that there actually is some difference between men and women in their preference for vanilla? Okay. So again, there was difference in our data. Was it enough to be statistically significant, or was it normal variation and fluctuation? The likelihood of getting those numbers was 22% chance to happen. Okay, and so again, what it is we pulled off an event that was 22% chance likely to happen. That's not uncommon at all, right? 22% is not that low of probability. Now, if it was like a 0.001% chance to happen and we got it, we'd say, well, that's weird. It was very unlikely for us to do that, but somehow we did it. That would mean that the null was probably wrong and there probably is some difference between the two proportions. But again, this was not lower than our null, so there's no reason to think there's anything wrong with the null hypothesis. So we do not get rid of it. We stick with status quo for now. Since our p-value is more than alpha equals 0.05, we do not reject the null. We would say we fail to reject the null. Doesn't seem anything wrong with it. The data does not suggest that men and women prefer vanilla differently. Okay, so there is insufficient evidence or you could say the data does not suggest, it doesn't matter. There's insufficient evidence to suggest a difference in preference for vanilla among men and women. Again, which is a pretty powerful test. I mean, okay, so maybe this isn't, saving lives or anything like that, figuring out a question like this, but this procedure works on any question you want where you're comparing two proportions, okay, two percentages. And again, when we look at the sample, to me, I would go, well, it does seem like the men like vanilla more than the women. It seems sort of like a big difference, but apparently statistically it's not big enough to say that the null is wrong. So there's no reason to assume that men like vanilla more than women or vice versa. It appears that that there's no difference there. Okay, that is it for this video. For the next video, we will, I know it feels like we're going backwards, we'll do the 10.1 material, which is to go back and do all these problems that have to do with means, okay? But you'll see, just like what we saw with this, that it's really, really similar to, it's identical, let's say, to what we did in Chapter 8 and 9. It's just that some of the formulas got twice as ugly, or some of the IRL steps got twice as ugly. Aside from that, this is why I was saying the better you know Chapter 8 and 9, the easier the rest of the class is, because all we are is doing those examples over and over and over again, just adding slight bits of elements to them. Okay. I will catch you guys on the next video, 10.1, where we talk about means in two samples.